in the sense that you want to be the memory on chip, okay, and not off chip, because if it's off chip, that it will influence both the access time and somehow the availability. And also you want to code the memory, okay, so you need this kind of integration and availability for electronic design automation tools, okay, in order to have the memory in its RTL design and so on, okay. And of course, and also you want the memory to be non-volatile, okay, so data to be stored indefinitely in that memory and so on. So because of these traits, okay, well, there is no memory technology that have low access time, non-stop availability, low cost, to be integrated on the same chip with other components, okay, and to have and to be coded with the other components with the RTL part, okay. So you cannot have all of this, okay, and that's why memory hierarchies are employed. So the fastest kind of memory are the registers and the register files, which are implemented with D flip-flops. Of course, it's very natural to integrate the flip-flops with the combinational logic components in any kind of digital circuit. Of course, there is no problem regarding the EDA tools, okay, so synthesis, simulation, implementation, and so on. It's quite simple. Of course, because there is this kind of strong support for EDA tools, they are easy to synthesize from RTL code. As I told you, the RTL code for registers, it's pretty simple, and of course any kind of digital design will contain the RTL code for that component. Because they are implemented with edge triggered flip-flops, they have very high cost per bit. So first of all, you have the edge trigger flip-flop has 16 transistors, okay. Secondly, for example, in the case of the register files, for each access port, it is required, will lead to 1.5 times cost increase, mainly due to additional circuitry required for each access port, not for the storage element. Usually they have small cost for logic required for data access, in the sense that if you have registers, there is no address decoder. If you have register file, then the address decoder, it's quite simple. And of course, you don't have additional circuitry, you just put the register, so you don't have, let's say, sense amplifiers and stuff like this, okay? So this is the register and register files, which are the memory embedded into the processing circuitry. Then you have the static RAM, which have high speed, and this is also due to the fact that they share as the storage element, the same storage element as registers, in the sense that SRAM are built based on cross-couple D-latch. I don't know if you remember from last year course, there are these two inverters in feedback, okay? That's the cross-coupled D-latch. Okay, if you employ a master slave, then you'll have with two D-latches, then you'll have an edge trigger flip-flop. If you employ, for example, NMOS pass transistors additionally and 2 lines, okay, 2 bit lines, then you'll have a static SRAM block. Usually it can be integrated with in the same chip with conventional logic, so they are actually SRAM nowadays is used on chip. Okay, you have 2 types. The most common type is the addressable SRAM. They are in the so-called scratch pad memories, and of course you have the content addressable SRAM, which are found into the cache memory. Okay, by the way, as a fast memory, it's you have this scratch pad, which with respect to the cache, the scratch pad, it's actually you can allocate, so it's visible from the programmer for the programmer, so you can allocate memory. Okay, you can have malloc there. Okay, in the cache, as I told you, you don't have. Okay, both can be synthesized from RTL code, so you can have from the design. In most cases, as you'll see, templates may be employed both for addressable SRAM and content addressable SRAM, and you will need, especially for ASIC, dedicated tools. Okay, dedicated tools means that they are more in the case of memory, they are much more expensive than conventional tools. So for the support for from the tools part, for FPGA you have built-in SRAM blocks, which are called block RAM or BRAM, and the FPGA tools actually will map the code corresponding to the SRAM on the PRAM. Okay, so it's quite simple mapping. As I told you, for ASIC, you have these dedicated tools used to synthesize and implement these memory blocks. So the main thing is using the tools and using these templates for SRAM, you will get the conventional SRAM block composed of SRAM self. Okay, if you use conventional tools for normal logic, then the result will be an edge trigger flip-flop based implementation. I know this. Okay, usually these memory tools are, let's say, something like 10 times more expensive with respect to conventional for logic kind of tools. Okay, so they are extremely expensive, with the result that it will end after the synthesis in 6 transistor and not 16 transistors. As I told you, there is this 6 transistors per cell. The address decoding, it's almost the same as in register file. So it's a simpler kind of address decoding. What it's actually, the difference is that some sense amplifiers are required for data read and data write. Usually these sense amplifiers are based on differential processing, okay? So you have these differential lines, meaning that you have, let's say, the bit line and the bit line negated. Well, for the SRAM, it's actually used when you need memories in the range of kilobytes and up to tens of megabytes or megabits, let's say. From kilobit to megabit or tens of megabit range, the SRAM memory is the one that you employ, which makes them suitable for quite a lot of applications. Okay, but for many applications, let's say in the video domain, it's not so good, because a high definition image you can store in a tens of megabit memory, maximum one image, and that's not a high definition, or with you need some form of compression there and some data loss and etc. Okay, so usually this is the range of application found up to tens of megabits of memory. Okay, so this is the addressable RAM. Of course, there is the content addressable RAM, where you need highly dedicated tools for ASIC, because different memory cell is used with respect to the addressable RAM, in the sense that you have a 9 transistor cell, not a 6 transistor cell. You actually have no support in FPGA, or little support. Usually it's mapped over existing VRAM and with some form of emulation logic on top of it. Okay, so you'll have the VRAM plus the emulation logic for the content addressable SRAM. Okay, the address part, the address, let's say address decoding, it's more complex. Okay, it's not a simple address decoding. Of course, you use the same sense amplifier, because the storage, the component, yet again, it's based on the cross-coupled D-latch, as in SRAM, as in the flip-flop. Dynamic RAM. Dynamic RAM, it's a 1 transistor per cell. However, this 1 transistor per cell versus 6 transistors per cell, okay, in the SRAM, so dynamic RAM has only 1 transistor, comes at the cost with quite a great range, quite a big range of disadvantages. So first of all, you have highly complex address decoding. You have row address, you have column address, so you need to somehow to split the address into giving actually 2 cycles. Okay, not quite cycles, but in 2 stages, the address with a row, with a column, and then you have some activation signals and so on. The sense amplifiers are quite costly. Okay, DRAM, it's because it's dynamic, needs, as I told you, refresh. Refresh is performed per line. Basically, refresh means that from time to time That time is given by counters, by the way. From time to time, you will need to read the entire line and to write it back. And actually, this process means that you will need to you have some logic for it, okay? So this is quite this means more cost, okay? Actually, this one transistor per cell starts to pay off only when several hundred of megabytes, or let's say memories, are employed. Okay, so actually this is the range of application when you go into giga range. Okay, otherwise both the cost and also the other disadvantage are not making DRAM. So let's say 16 megabit DRAM, it's nonsense. Okay, DRAM cannot be coded and synthesized and implemented from RTL code, and it's not integrated with logic most of the time. Usually they come, it's an off-chip memory, and also because it's off-chip, you have different disadvantages such as lower speed. Okay, actually DRAM consists on the fact that the data is stored on a parasitic capacitor there, so you have this lower performance with respect to SRAM. Also, because it's off chip, you have lower performance because when you go out of chip, you have more these parasitic traits, like parasitic components like the resistors, the capacitance, and so on, are much higher if you're talking with the on chip. Okay, and that makes the memory slower with respect to the SRAM. As I told you, a big problem is this refresh. Okay, by the way, for example, to tell you something about the refresh, I made say 6 or 7 years ago an DRAM memory controller. It's something, one of the it's very difficult to make the DRAM memory controller on an FPGA which you can access the DRAM. Okay, and one thing about the DRAM memory controller is that you have a range of frequencies. Okay, so basically an SRAM, you can use it for example, the SRAM, let's say it has a maximum frequency that you can access the SRAM 100 megahertz. I'm giving you an example. Okay, and as long as the frequency for the access is lower than 100 megahertz, everything is okay. Even if you're going into, let's say, 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz, and so on, it's okay until you go till 100 megahertz. In DRAM, you have a range, meaning that you have a maximum frequency and a minimum frequency. Yeah. So basically, in DRAM, you can have, let's say, a 10 to 18 megahertz. It's not okay if you go with, let's say, 1 megahertz frequency if the lower frequency of the DRAM is 10 megahertz. Do you know why you have problems if you go with a very low frequency for the DRAM, you have problems in the sense that data becomes corrupted. Okay, why do you think it happens? This is because the refresh cycle, okay, you have to perform refresh at, I don't know what time, okay, so at let's say 0.6 seconds you have to perform one refresh, okay. So how do you measure this 0.6 second? How do you measure this, let's say 0.6 seconds? Well, you measure the same as you have in your project, your lab project, okay? Use a counter and you count the clock ticks, okay? And actually, if the frequency is lower, of course, that counter will give not 0.6, it will give a higher time constant, okay? And actually, you are not performing the refresh during this 0.6. You're performing, if you're using a lower frequency, at let's say 0.8, which is may not be enough for the refresh, and data will become corrupted. Okay, so the DRAM has this lower and a higher range frequency. Yeah. Now, non-volatile flash memories. Okay. First of all, these are off-chip, okay, because they are off-chip, they usually come with a specific controller. And first of all, well, the flash memory, okay, or the non-volatile semiconductor memory relies on a so-called floating gate per cell. And usually to have this, especially for the write, you need to apply different voltage than the conventional VDD, okay? So you, because at right, okay, you will need to have different logic perform read and the write operation, and so regarding the randomness, okay, every read has the same latency no matter the address. Every write has the same latency no matter the address. However, there is quite a big difference in the between the between the read and the write. So basically, if you're performing a read and write at the same address, the access time is okay, it's not the same. For the write, it's actually much higher, okay? Because of the floating gate, actually the floating gate has this problem that okay, some voltage potential may become trapped into this gate, and actually the threshold voltage will start to shift. Actually, you will the flash memories are not so non-volatile. Okay, so there are many applications where are not considered a non-volatile memory. Okay, for example, if you want long-term storage, they're not considered pure non-volatile memory. Okay, and one thing it's okay, they have a very slow corruption rate, and that's why every flash memory needs error correction. Error correction nowadays it's performed either with BCH. By the way, have you done error correction codes and stuff like this?
I think we talked about a little error correction at the computer architecture class, something with checksum, XOR, but not much.
So not about codes and so on. Well, let's in the last years, that's my let's say specialty. Okay, ECC. Okay, especially LDPC. Okay, I've worked with guys that work on LDPCs for LDPC come from low density parity checks, with guys that have made the startup for LDPC for flash memories. Okay, and actually that startup, it's well, it's in the state, and it's now I think it's $5 million dollar valuation kind of thing. Okay, so yeah. So this is with error correction, and depending on the application in this controller, you may have compression processing, so compression accelerators. Okay, you may have cryptographic accelerators. Okay, so yeah, well, it depends on the you may have other compression part, crypto part, and so on. Okay, the error correction, it's mandatory. Okay, and yeah, okay. So as I told you, the cost, it's one floating gate per cell. Because flash memories do not generate so much heat, okay, per time, you can apply 3D stacking. Okay, 3D stacking, it's actually putting planes of silicon one on top of the other. Do you know what's the main problem with 3D stacking? So the main problem with 3D stacking, it's the fact that okay, you have this intermediary layers, okay, and if you have, let's say, let's consider a GPU, okay, and you apply 3D stacking on the GPU, you know that one thing about the GPU is that it heats up consistently. Okay, so basically with these intermediary stack layers, the heat cannot be dissipated. Okay, from these intermediary layers. Yeah. Okay, so these are characteristics for non-volatile flash. Next course we will have, I will give you two examples. First example, it's well, these are the highly used and the ones which are RTL coded. The SRAM addressable, which you will start also this week at the lab. And we'll have an example for the SRAM addressable with many port configurations. And also we will have an example for memories which are widely used, the queues. Okay, I think that the queue principle you have also used at the operating systems. You had the pipes between several processes. Am I right? Did you have the pipe? Did you make the pipe in operating systems in order to communicate between processes?
Yes, we talked about pipes.
Okay. Have you implemented or have you coded?
Yes.
Okay. So you're not just talking. Okay. Okay. So this kind, which the pipe actually was more or less like a queue. Okay. By the way, do you know why queues are very good for communication between different, let's say, components?
Because of the first in, first out principle?
Well, yes, because of this, because these are queues, but why do you think they are important and quite easy to, let's say, not to implement, to use them?
You only need to access the top of the queue.
So basically, just to explain, the sender and the receiver do not need to know the status for the other one part. Okay. So the receiver doesn't need to know what is doing actually the transmitter. Okay. The sender. You just need to know, okay, the queue is not empty, then I can read from the queue. Okay. And of course, you will read in the order that the sender has sent you data. Okay. In the same order. Okay. And of course, the sender doesn't need to know whether what is the internal status of the receiver. Okay. The queue is not full, then I will send him the data and he will receive it sometime in the same order as I'm giving him. Okay. And actually this makes queues very useful for this kind of asynchronous communication. Okay. Because you don't need to have any kind of handshaking between the sender and the receiver. And I'm not talking about only the hardware part, it's actually also between processes and threads and so on. Okay. Okay. So next course we will talk about the SRAM, the coding for the SRAM, and the coding for, in this case, the synchronous FIFO. Okay, or the synchronous queue. There is also asynchronous queue, which is also highly used. Okay, in digital design. Okay, so yeah, this is for this course. Also, as I will told you at the lab, for the project we will proceed with the memories, and I will explain why. Okay. Which relates mostly to the fact that I'm hoping that we're going to have some 3 or 4 labs on the face-to-face, and you'll put your design on the board. Okay. Okay. If you have questions. Okay, if you don't have questions, I will. Please don't forget about the exam dates. Okay, I'll wait by Monday. The confirmation for the exam dates. Okay.
Okay.
Okay. If you don't have questions, then we'll meet the next Thursday at the course. Thank you.
Goodbye. Have a nice day.
Thank you.
Bye.
Bye.
Nice day, goodbye.